All right. Today we will talk a little bit about the oscillators, and in particular the stability of oscillators. What we mean by stability of oscillator is the frequency stability. So what does that mean? So think about it, if you think about an oscillator in time domain. In time domain, an ideal oscillator will have a waveform that will look like the solid waveform in the top row, right? I mean, so what you see is if you connect an ideal oscillator to an ideal oscilloscope, what you will see is that you will see that there's a triggering happening here, and you will see that the edges will happen exactly at the same time, because with the same equal interval. So since the oscilloscope overlays multiple samples of the waveform, you will see that the edges will happen exactly at the same time. Now in practice, if a practical oscillator will not exhibit that. A practical oscillator, what it will do is basically, if you look at it, the first triggering edge may be pretty sharp, but the subsequent one becomes a little bit fuzzier, because every time the period can be a little bit shorter or a little bit longer. And if you overlay them on top of each other, what happens is that you will see a spread. And this spread actually grows. So what happens here is that the longer you wait from the edge that you triggered, the more of this fuzziness you will see. This is called timing jitter, or clock jitter. And it has actually interesting properties. We'll see why it does have these properties later. But if you look at this, for example, if you plot a histogram of the transition time at the threshold, you will see that you will have a spread that grows. And if you plot the variance, for example, you will see that the variance grows linearly first and then quadratically, which basically means that it's a standard deviation that's growing linearly. So this is a time domain picture of the oscillator instability, or instability, frequency instability in an oscillator. And why does this matter? For example, if you have a digital circuit. If you have a digital circuit and you're trying to use this clock to trigger a flip-flop, something as simple as that, right? The flip-flops have setup and hold times that you need to maintain to make sure you guarantee proper operation. But then you need to add this in uncertainty, this timing jitter to that, because your clock can happen earlier or later by that much. So you need extra margin, which means that you cannot operate as fast as you could if you have a very noisy clock, something that has a lot of jitter, because then you need to have a larger amount of margin in the system. Now, the same oscillator, if you look at it, what does this frequency stability, instability look like in frequency domain? So if you take the same oscillator and connect it to an ideal spectrum analyzer, right, and look at the spectrum of what comes out, what you will see is that in an ideal oscillator, you should see a sync in terms of frequency content. If it's a pure sinusoid, you should see an impulse, right? All of your energy is concentrated at one frequency and one frequency only, F naught, and nothing else. But in practice, if you take a real oscillator that has frequency instability, you will see that the energy is actually spread in this Lorentzian-shaped, bell-shaped energy. So the total energy, by the way, underneath this would be about the same as the energy under that thing, but but what happens, or the power, more accurately, but it's spread across multiple frequencies, right? So its frequency content is not single frequency because of this frequency instability. So why does that matter? Well, think about, there are many examples that it matters, but just let me give you one example. Let's say you're trying to make a receiver. In a receiver, you have an antenna that basically receives the signal from the air, and then you have an amplifier, right? You have an amplifier, a low noise amplifier to amplify it. And then the next thing you do is just basically you multiply it typically with a local oscillator, LO, to down convert it to a frequency of operation. Either it's a baseband frequency or IF frequency, intermediate frequency, doesn't matter. Now imagine that you're trying to recover a weak signal in the presence of a strong signal, adjacent to a strong signal. So you have a weak desired signal in presence of an adjacent channel, right? So for example, this may be a scenario where you're trying to receive a signal from a far transmitter where there's a nearby transmitter transmitting in an adjacent channel. Now, what happens if your clock, if your LO, is not pure, the spectrum of this Lorentzian shape will get, of course, in time domain they are multiplied, so in frequency domain it gets convolved. So these two will get convolved with those two channels. And you can see that your desired channel can get, what we say, can get buried under the phase noise skirts of your blocker. So you can see what happens is that your signal can be either completely buried or its signal to noise ratio can be significantly degraded. So this is the same thing. This is the same frequency instability in frequency domain or time domain, two examples of that. Now, how do we measure, how do we quantify this? One of the very famous ways, or one of the common ways of quantifying this quantity is phase noise. Now, what is phase noise? So if you look at the power of the total power under this bell-shaped curve, and then you look at the center of this thing, the center frequency, the nominal frequency, let's say omega 0 or f0, and then you go an offset delta omega or delta f away from that and use a bandwidth, certain bandwidth, let's say for the sake of argument 1 hertz bandwidth, and then measure the power in that and compare it to the total power underneath this bell curve. That would be obviously a smaller fraction, right? So it would be a negative quantity. And this is what we call dB. It's a measurement in what we call dBc, dB with respect to carrier, because this is the total power is the carrier power, right? So it's that measured in dBc. And then if you normalize it to the bandwidth, it would be dBc per hertz. So this is a quantity that you measure in dBc per hertz. And it is measured, and if you plot this quantity versus the logarithm of this offset frequency. So if you take this offset frequency delta omega and plot this quantity versus the logarithm of that, typically for most oscillators, you will see 3 different regions. You see a region where you have a slope of negative 30 dB per decade. We call it 1 over f cubed region. We see a region that has a 1 over f squared drop. And then you will see a region that has a and then it eventually becomes flat. The question is that why do you see this, and how do you quantify this, and why does it? How do we quantitatively determine it? And then one of the things that matters is this frequency. This is basically where the asymptotes of the 1 over f squared and 1 over f cubed regions intersect, right? Intercept. And then what happens at that point? We call this omega 1 over f cubed. That's the corner frequency associated with that. Now, what is causing this thing? There are several different things that can cause frequency instability. Some of them are what we call the intrinsic noise sources. We talked about noise sources before. There are thermal noise in the MOSFET, the shot noise in the bipolar transistor, the flicker noise of the device. And these can have different profiles, right? I mean, if you can, for example, the spectrum of the noise itself can have a 1 over f region and then a flat region. 1 over f region due to flicker noise, and then a flat region due to white noise, or it can be thermal noise, something like that, which we approximate as white noise in the frequencies of interest, right? So they have a spectrum like this, and each one of them have their own corner frequency, omega 1 over f, or f1 over f, the 1 over f corner. There are also extrinsic noise sources, also known as interference, right? So what we call, for example, let's say you are making a chip that's, has digital circuitry, a large digital circuitry in next to analog circuitry. You have an oscillator on a chip that's large, and there's digital circuitry running. So when you have digital circuitry running, there is current switching that's happening, right? And then the current you draw, for example, from the supply and ground is going to be different at different times. It's fluctuating, and since there's a non-zero impedance on the supply and ground, as a result, what happens is that you will induce some fluctuations on the supply and ground and also on your substrate that can couple back into your circuit, into your oscillator, and induce fluctuations in it. So that's also another source of frequency instability. So the key question is, there's a kind of like a pretty famous known model from 1966 called Leeson Cutler model, LTI model, for this, trying to explain at least part of it. So the Leeson Cutler model is what we call a semi-empirical model, in the sense that there are certain aspects of it that are captured theoretically, and certain aspects of it that are based on certain assumptions and hand-wavy aspects. But anyway, it's a very valuable thing. So what it says is that it says the phase noise, which is shown with this like L of delta omega, can be described with the following expression. So where you have kT, which is the Boltzmann factor times temperature, divided by the oscillator power, the power that's kind of circulating inside the oscillator, times f, which is a fitting parameter essentially, which is like we call X noise factor. It's a fudge factor. Then 1 plus omega 0 over delta omega, where delta omega is that offset frequency and omega 0 is the center frequency. QL is the loaded Q, quality factor of the resonator. And then there's this other term that says 1 plus omega 1 over f cube over delta omega. In fact, the Leeson assumes that omega 1 over f cube is equal to the omega 1 over f of the noise source itself. You remember when the flat noise became the white noise? And we'll see that that's not correct. And we'll see that, in fact, it is related to it, but it's not equal. And we'll see how it's related to it soon. So where does this come from? The 1 over f squared part of it, it can be modeled in this way. So if you think about an oscillator, you can think about it as an RLC network. So the one way to make an oscillator is an RLC oscillator. There are other kinds of oscillators that this model does not capture. And we'll talk about those too, like ring oscillators and relaxation oscillators and Bose oscillators. But let's say you have an RLC, a resonator-based oscillator. And an RLC can be modeled as an ideal L, ideal C, and some loss, some element G, some conductance G capturing the loss. Now, the way you make an oscillator is that basically one way to make an oscillator is to introduce an active device that presents a negative conductance or negative resistance that cancels this positive resistance and makes this into an ideal LC. But the interesting thing is that, yes, you can, the negative resistance can cancel the positive resistance, but the noise of the positive resistance and the noise induced by active device are going to be uncorrelated, right? Because they're generated by two different sources. And as a result, they will not cancel each other. They just basically add to each other because they're coming from two different sources. Although the conductances are canceling, but the noise sources are not. So this noise source, this aggregate noise source of combination of the noise due to this and due to that thing, will be something. So let's just take into account for now the noise of the resistor by itself. If you take the noise of the resistor and assume some sort of a 1 over f noise behavior coming in from somewhere, this is going to be the spectrum of that noise, right? This is the spectrum of this current, the current source being injected into the oscillator, this top plot. Now, what you have is that this current is converted to a voltage, right, through an impedance. That's the transfer function. And that transfer function is simply calculated, it's basically the impedance of this LC. And you can approximate it as, you can write it in terms of, as a function of omega naught plus delta omega, as an offset from omega 0. And you will see it would be 1 over g omega naught over 2ql delta omega. And basically what it does, it means that the noise here goes through this filter, right? That's shown, this transfer function, the second plot, and would produce something like this. Now, there are a few things that are missing. So one question is that how does the noise from here get up here, right? Because it's this noise, the noise from the low frequency, how does the noise from low frequency get up to the high frequency? The noise from the middle, around the omega naught, you can see it's going through this transfer function. The other thing is that why does it become flat? Why doesn't it go to infinity? Because that transfer function goes to infinity at omega naught. And why does it flatten out and generates this bell-shaped curve as opposed to something completely flat? So those are some of the interesting questions that arise. Now, there's another viewpoint that we'll look at next. And this is a little bit of a slightly different viewpoint, just like a few slides on that, to kind of give you a little bit of an intuition about the oscillators. So if you have an resonator and an oscillator, and if you take this resonator and make an oscillator with it by introducing a negative resistance in parallel, what happens is that if you have the resonator by itself has some sort of an impulse response, right? And the impulse response or step response will have a decaying sinusoidal response, typically. And the rate of decay is determined by the quality factor, how much energy you lose. Now, when you put it in an oscillator, this does not decay, right? So you expect the line width to narrow, but the line width does not narrow to 0 because of the fact that you have some timing jitter. You have some phase noise, right? It's not going to be exactly. Now, the question is that how much does it narrow, and why does it narrow to begin with? How can you kind of think about it? If you have something that looks like a decaying sinusoidal, you expect it to narrow down, right? The line width to have some line width. Now, we want to see why an oscillator whose amplitude does not decay would exhibit a similar behavior. And that brings us to the concept of virtual damping. So this is more of a thought experiment, if you will. So imagine that you have an ensemble of n oscillators, right? That they're identical in terms of component values. So all of them have exactly the same component values, right? And you start them at the same time. You just turn them on in the same phase. So at time t equals 0, you expect them to be, if you take the waveforms of these things and overlay the waveforms, right, what would you see? You will see that they are all on top of each other. But they have different noise sources, right? They have the noise sources have the same statistical properties, but it doesn't mean that they have the same exact value of noise. So each one of them deviates in a slightly different way. So as time elapses, you will see that more and more they deviate from each other, right? The waveforms. Now, if you look at the expected value or ensemble average of this group, what do you see? You will see that over time it's basically decaying, right? Because the ensemble, the average of all waveforms that are exactly on top of each other is going to be larger than the ones that have deviated from each other. And the more they deviate from each other, the more you will, the reduction you will get. And in fact, you can actually show that it becomes a decaying exponential. Now, this is an actual experiment here, for example, where you take, what we've done here, we've taken this, instead of multiple oscillators, in this case 512 oscillators, we've taken the same oscillators and taken 512 samples of its waveform at different times. So we have replaced the ensemble average with time average. So there are some assumptions here being made. But if you do that and take 512 samples of the oscillator waveform and just overlay them, add them, you see exactly this exponential decay. Now, here, to make it observable, we have introduced a lot of extra noise, because normally this would take a long time for it to decay. In a good oscillator, that's what you expect, right? So this is just to make it more pronounced and demonstrate it. That's what we can do. And then basically, based on that, you can actually calculate what your rate of decay and a phase noise is. There's a simple relationship that describes the phase noise in terms of this rate of decay. In fact, if this decay rate, if you look at the damping rate, d, it would be just simply 2d over delta omega squared, and describes the 1 over f squared drop of the noise. And then this basically tells you that there's a line width narrowing happening, or line width enhancement happening, due to this basic reduction or virtual damping. But the line width is not going to be 0, because there's still a decaying expected value of the ensemble exhibits a decay in the effective average of the thing, which is at a much slower rate. Okay, so this is another viewpoint, again, to give you a little bit of sense. But now, what we're going to do next, we are going to develop a framework for studying any oscillator of any type, not necessarily just RLC oscillators and things of that sort, that allows us to make quantitative and accurate predictions about the oscillator, and also make gain design insights. So this is yet another viewpoint. So in this viewpoint, you can think about an oscillator as a box, as a noiseless box that has multiple inputs, and the inputs are the noise sources in the system, right? So if you think about an oscillator and you have multiple noise sources in the system, what happens is that these are the noise sources that can be intrinsic or extrinsic noise sources. Now, an ideal oscillator should produce what? Should produce a waveform that is some constant amplitude and some, for example, cosine of omega naught t plus some constant phase. Now, a real oscillator does what? It can have amplitude that has fluctuations. So the amplitude would be a function of time, right? As well as the phase itself. The phase also can deviate. So they have amplitude fluctuation and phase fluctuation, amplitude noise and phase noise, and the waveform may not be sinusoidal exactly. So there's this deviation. So the black waveform here, for example, presents the ideal waveform, and the red waveform shows an example of the deviation. Now, the next slide is an important slide. So this picture is very important. Now, even for an ideal LC oscillator, which is probably the simplest kind of oscillators, one of the simplest things you can think about, the response of the oscillator's phase to perturbation is time varying. What do we mean by that? So think about this simple example. If you have a parallel LC, ideal L, ideal C in parallel, and you have a current source in parallel, which is 0 at all times except for t equal tau, right? So the input is delta of t minus tau. And it comes in, and the impulse hits the oscillator. So the oscillator is already, there's a waveform. There's some energy in the tank, in the oscillator, and it keeps going back. It produces a perfect sinusoid, right? The black curve. Now, as you at some point in time, you inject an impulse into this. Now, what is this impulse going to do? The impulse is going to go entirely through the capacitor, and it's going to instantaneously change the voltage across the capacitor because it will inject charge into it, right? So it will change the voltage by some amount, which is basically, if your injection is delta Q, then it will be delta V that's proportional to delta Q divided by C. Q is CV, right? Yeah. And then, so now, imagine two scenarios. Scenario number one is when the injection happens at the peak of the oscillation, right? So let's say the injection happens at the peak of the oscillation. What will happen? you will see that the amplitude increases. That's when the capacitor was fully charged, so you increase the charge, right? And the oscillator will go exactly in the same phase. Now imagine that you inject the impulse at a different time. Let's say at sometime near the transition time. And now you can see that it induces a phase shift as well. And in fact, there is a point at which you can actually inject an impulse and change purely the phase and not the amplitude at all. So let's think about that point. If you think about that point, if you view the oscillator, you can also view the oscillator in the state space, right? For example, if you have an LC, you can look at the V and I, the V of the capacitor and the current of the inductor. And if you look at it, the oscillator is going through a closed trajectory, right, in the state space. This is the state space picture, right? So when you inject an oscillator with an impulse, let's say, for example, here, and you push it here, what you're doing is that basically, so let's say this was the waveform of the oscillator. So this is the original waveform of the oscillator. Now, if you inject an impulse at this point and bring it down here, you have essentially advanced the oscillator, the time. You've done essentially time travel. You've jumped from one state to another state. And if you hit it, let's say, at this point and bring it up here, then you have essentially, I'm sorry, in this case you have advanced or pushed it back in time. But in both cases, so let me just maybe use my color code correctly. So this is basically just the red is when I have put it in a point farther down, and the purple is when it's going this way. Now, if you do this, what you see is that there's this instantaneous change in the phase, in the state of the oscillator, without any change in the amplitude. And you may come back and say, wait a second, how is that possible? How is the energy of the oscillator not changing at all? Because I'm injecting current into it, right? Well, injecting charge is not equivalent to injecting, or injecting current is not necessarily equivalent to injection of energy, right? The energy, the power is determined by the product of the voltage and the current. The delivered power is P is V times I. So when you do this, you're going through a transition for half of this cycle. For the first half, you may be injecting energy, and you're taking the same amount of energy out in the second half. So the net energy injected is 0. So you can have a impulse injection which has exactly 0 perturbation to the energy of the system. So anyway, the key takeaway from this view, from this experiment, or thought experiment, is that even an ideal LC oscillator is a time-varying system as far as the phase is concerned. And you may come back and say, wait a second, this is an LTI system. How can it be time-varying? The capacitor and inductor are LTI. How did you get a time-varying system from this? Well, they're LTI for voltages and currents. They're not necessarily LTI for other variables, right? So if, for example, if I determine the temperature of this thing as the output, would it be remaining LTI? Not necessarily. So it's a function of not only the components, but also the choice of the input and output variable. So now the output variable we are looking at is phi, the phase, not a voltage or current. And hence, it's OK for it to be non-LTI. In fact, in general, it's even not even linear for large perturbations. So that's for that. But now, of course, if you think about it, like we said, we are traversing in a state space. Now, a realistic oscillator, a properly designed oscillator, what it does is that if you deviate its amplitude, right, if you introduce some amplitude deviation, it will recover that amplitude, right? It will restore its original amplitude. Because if the oscillator was originally had a stable amplitude, it meant that it had some internal built-in feedback mechanism that would bring its amplitude back to that level. So if you increase the amplitude beyond the steady state amplitude, it will eventually go back to its steady state. Or if you decrease it, the same thing will happen. So in state space, the way it's described, we call this a limit cycle. In state space, in that trajectory that you traverse, it means that there's a trajectory, there's an ideal orbit, there's a stable orbit. That's what we call it, right? Which if you deviate from that, you eventually go back. So the amplitude fluctuations get suppressed, even in a realistic oscillator. But the phase fluctuations will not. because the oscillator has no way of knowing its previous phase, right, when you hit it. So the phase fluctuations will persist. And you can see this. For example, this is a ring oscillator. Now, this is another example. So, and this, you can see this is generally true. This is not necessarily limited to LCs. So this is a ring. This is a 5-stage inverter chain ring oscillator. So if you take 5 digital inverters, CMOS inverters, and put them in a chain, it will oscillate, right, at some frequency. Now, if you inject some charge into one node, and you can see, depending on when you inject it, for example, if this injection is happening at a time when the stage is saturated to one side or the other, then you can basically get very little phase shift, right? And amplitude fluctuations is dissipated very quickly. But if you inject it during a transition, you will see that actually you get a lot more phase shift. Now, you can actually quantify, so since the delta V is the change in the voltage, the jump in the voltage is proportional to the injected charge, delta Q, which is the area under the impulse, divided by the capacitance on that point of injection. You can also express it this way. So you can see that there's a time-dependent proportionality factor for the phase shift with respect to the injected charge, right? So if you have an injected charge delta Q, you can normalize it to the Q swing, which is maximum charge swing on that node. And then there's a proportionality factor, which would be unitless, essentially. You'll have units of radians, which is unitless, by the way. Radian is no unit, because radian is the ratio of 2 lengths. It's the ratio of the arc to the radius, right? So it's basically will be, and you can show this proportionality factor as gamma of omega naught t. You can actually think, so it's a function, it's not a proportionality constant, it's a proportionality function that changes with time, and it's a measure of how sensitive each point in the waveform is to a perturbation for phase, right? How much phase you get at perturbation. So you can imagine that this function, which we call the impulse sensitivity function, because it's a function that captures the sensitivity of this the oscillator to an impulse, right? So it makes sense to call it impulse sensitivity function, or ISF for short, would be larger, for example, in this example, during these transition times, and small during the times when the stage is saturated to one side or another for this node. And each node will have its own impulse sensitivity function, or each source, more accurately, will have an impulse sensitivity. Now, this is not even limited to the ring oscillator. So this is yet another kind of oscillator, right? Which the Bose oscillator, right? So if you take an inverter, this is probably one of the simplest oscillators you can make. If you can make an inverter with hysteresis, right? And take that, and if you just apply an RC circuit in parallel with this, what happens is that you can produce an oscillator that basically transitions, goes exponentially up and down, up and down. And then so what you can see from this picture is that if you now instantaneously apply a perturbation, if you introduce a sudden change in the voltage due to an injection of impulse, that would correspond to a shift in time or shift in phase, right? And again, you can see that this oscillator will have its own ISF for this noise source, meaning that a change, an injection in charge normalized to the maximum charge swing would correspond to a certain amount of phase shift, which is proportional, determined by this, again, and yet another gamma, another ISF, impulse sensitivity function. So is this true? Well, you can actually run tests and experiments and verify that experimentally. You can basically see that you can run simulations for different amounts of charge, and you can see that actually for injections many orders of magnitude larger than what the actual noise looks like, there's pretty linear, right? This relationship is pretty linear. Now, and then you can verify that also in other ways, experimentally. You can basically make an oscillator and make multiple like double the size of everything, and you will see that the perturbation to an injection the response to a perturbation would go down exactly as 6 dB, which is what you expect from a linear response. So all of this leads to this next concept, which is an important concept. So it says, if you can, so this is the kind of culmination of that discussion. It says that if you take an oscillator, you can think about an oscillator as a system with an input that's current or voltage, and an output that's the phase of the oscillator. You can characterize it. We saw that for perturbations that are sufficiently small, which noise definitely qualifies for that. The noise response, it's a linear response, but it's a time-varying response. So now you're dealing with a linear time varying system. Now we know from the linear system theory that a linear time varying system can be characterized by its impulse response entirely, right? So what is the impulse response? Well, based on what we did, the impulse response is essentially the ISF, which is a unitless function with a period of 2 pi, the way we've described it, normalized by Q max, maximum charge swing, and times u of t minus tau, a unit step at time t equals. So it means that the impulse response of the system is a step, but a time varying step, right? So if you have a time varying step as the output to of the oscillator, what does that tell you? It tells you that, first of all, the fact that you have a step captures the fact that the oscillator has no memory of its past phase. Once you change the phase will persist. It will not go away. There's no restoring mechanism for phase to bring it back to previous phase it had. And the time variance of it is captured by the fact that the height of this impulse depends on the time of injection. And therefore, you write it as h of t and tau, not h of t minus tau, which would be the case for a linear a linear time invariant system. So how do these ISF look? How do these impulse sensitivity functions look for different oscillators? So for example, if you have an LC oscillator, in the case of an LC oscillator, you can actually show it analytically that if you have a cosine waveform, the ISF is going to have the form of a negative sign. It will be a negative sign, which makes sense. Remember, we had the most sensitivity during the transition times and the least sensitivity at the peaks to the phase, right, to the injection. Now, for a ring oscillator, it will look a little bit different. It will have these like lobes that will happen during the time of transition. And this may incorrectly lead us to conclude that it is the derivative. Now, it is not the derivative of the waveform for the following reason, because if you make something, if you look back, for example, at the Bose oscillator, and think about what would happen if the slope increased. Right? If the slope was higher, for the same delta V, would we get larger or smaller amount of delta phi? Smaller. Now, is the derivative larger or smaller? Larger. So you can see that it's not the derivative. It's somehow related to the derivative, but it's not the derivative itself. So let's not draw that conclusion. But it is what it is. It's some function that describes all of this behavior of the oscillator and its response to the phase. Now, if you have this impulse response, if you have the impulse response of an LTV system, linear time varying system, you know everything there is to know about it, right? So we can actually take advantage of that and write this, what's the master equation, which is basically the superposition integral. And if you plug this in there, if you apply the superposition integral to this impulse response for an arbitrary perturbation I of t, right? So if you, now instead of an impulse, if you have an arbitrary input I of t, then the output phase is given by this integral, which we can call the master equation, which is basically 1 over Q max, normalization to the maximum charge swing. You may or may not want to keep that. Sometimes we absorb it into the gamma to make it simpler. Gamma of omega naught t I of tau d tau. So we are integrating over that. So now what this means is that the oscillator, the process of phase noise, the evolution of the phase noise can be described with this system. So you have an input current coming in. It gets normalized by Q max. It gets multiplied or modulated by a periodic waveform, not sinusoidal necessarily, but periodic waveform, gamma or the ISF. That produces this function psi of t, which goes through an ideal integration to produce phi of t. And then eventually said, but that's the phase. What you measure a lot of times is actually not the phase. You're measuring the voltage of the output. So you have another process of phase modulation, which is a nonlinear process. So you have a linear time varying system followed by a nonlinear system to produce the output waveform. And we'll use this model to analyze the oscillator and draw conclusions about certain aspects of it. Now, you can, of course, think about what happens if you have different kinds of perturbations. So if you have now, based on this model, so these are a couple of examples. So let's say you have an sinusoidal input around the frequency of oscillation or an integer multiple of frequency of oscillation, right? So if you have a sinusoidal perturbation at n omega naught, in this case, n is 1, really, the way it's shown in this plot. but it can be any. What happens is that what you're looking at is the integral of the product of these two in time domain, which basically means that the convolution of these in frequency domain, right? The first and second plot convolve to produce the third plot and then go through integration. You can see because of integration, it's only the low frequency components of this thing that will survive, right? Because you have an ideal integration that will basically suppress anything that's high frequency. And it's shown with that profile, that 1 over f squared profile. So the only terms that would produce the convolution of the only two impulses, and of course the second line is the Fourier transform of the impulse sensitivity function, the ISF, right? Because what it is that since it's a periodic function, it would produce only impulses at integer multiple. So what you see is that the only thing that's left from this the only dominant term, the only low frequency theorem that you can generate is the interaction between the nth harmonic of the ISF. In this case, since n is 1 in this example, it would be C1, which is the fundamental component of the ISF, and the injection current, right? So these two impulses, the ones on the right, would produce a low frequency impulse here, and then these two, the ones on the left, also produce another one. So those are the only ones that will produce anything of significance. And then, of course, this is the spectrum of the phase. And then you go through a phase modulation. So basically, this will modulate the spectrum around the frequency of oscillation. Now, likewise, now this also shows you how a low frequency perturbation can produce modulation in the oscillator, right? Why is this important? Because you remember we didn't have a good explanation of what happens, why the 1 over f noise, for example, the flicker noise, would show up in the spectrum of the oscillator. When we were looking at the Leeson model, for example, right? We saw that it's a noise in the vicinity of the frequency of oscillation that goes through that filter. But it didn't really explain how the noise from low frequency came to high frequencies, right? But now you can see what happens. What you can see is that if as a surrogate for a low frequency noise, imagine that you have a low frequency sinusoid. The low frequency sinusoid in frequency domain will look like two impulses, right? At plus and minus delta omega. And then the only term that would interact with them to produce a significant result after integration is the C naught, which is the DC value of the ISF. So it says that the DC value of the ISF, right, is responsible for producing, for upconversion of low frequency noise to high frequency noise, to phase noise. And of course, then after this modulation happens, then you go through the PM to produce the sidebands around the frequency of oscillation. And this can be seen in this, for example, in a simulation too, right? What you see in the simulation is that you have injections at frequencies of oscillation, around frequency of oscillation. So let's say this oscillator is running around 1 gigahertz. So this is 50, you have an injection at 50 megahertz above that. So it's 1.05. You will see it produces those two sidebands as predicted, and some other ones because of the PM. And you can see a low frequency injection also does produce that. So on the left, you see the effect of low frequency injection. And you see on the right, you can see the effect of similar magnitude as a high frequency injection at f naught plus delta f. So it's the injection at this frequency, above delta f above f naught. And then it produces two equal sidebands, which is interesting. You have injection at one frequency here, but you get two equal sidebands on two sides through the process that we described. And this can be verified experimentally to be the case. Actually, you can actually run experiments with, and you can see that at all integer multiples of the frequency of oscillation in the vicinity. So it's a noise in the vicinity, or the perturbation is in the vicinity of integer multiples of the frequency of oscillation that would produce the most perturbation to the phase, right? And you can see this again experimentally. You can see that it behaves as you expect. It's 1 over f squared because of the integration, et cetera, et cetera. And you can actually make a prediction about this and compare it with the results. So you can make a prediction based on the value of the ISF. So you can actually determine the ISF and find its Fourier components, right? From the DC to fundamental to second harmonic, third harmonic. So these are like constants, right? And then use them, using this model, to predict what the sideband level would be. And then you can also directly inject a sinusoid and compare these two. And when you do that, you will see that actually they are very closely matching each other. So what about noise? So this is what happens to the perturbation, to a sinusoidal perturbation, right? What if you have your input is white noise? Now, if your input is white noise, again, you can go through the same process. And assuming that you have a white noise spectrum of IN squared over delta F, the phase noise for white noise perturbation is determined by the spectrum of the noise itself, obviously, the RMS value, root mean square value of the ISF squared, or the mean squared value of the ISF, and normalized to Qmax, which is the maximum charge swing. Intuitively, why would the RMS value of the ISF be the parameter that matters? If you think about it, it should be rather clear, because it's basically, we said it's the noise in the vicinity of the integer multiples of the frequency of oscillation that come into play. And they were controlled and adjusted by basically different coefficients of the ISF, the Fourier coefficients of the ISF. Now, the sum of the squares of all the coefficients of the ISF of a Fourier by Parseval expression, by Parseval equation, is the RMS value, right? In other words, if you actually write your ISF, you can write it as a Fourier series, right? In this form, for example, right? You can say gamma of omega naught t is C naught, which is the DC component, plus all of the higher frequency components. So C1 is the fundamental, the weight of the fundamental, the weight of the second harmonic, the weight of the third harmonic, and so on and so forth. And what happens is that if you have something like that, and if you take each one of them and get the magnitude squared, because we are dealing with noise, they're adding these powers that are independent of each other, then you will get the RMS value. Now, if you do this expression and then plug this form of ISF into that master equation, the integral that we had, and switch the order of summation and integration, which in this case you can do, this is what you will get. This looks like a bigger equation, but what it means is that that system that we described earlier can be even simplified more in this format. What it is that the input is coming in, gets normalized by Qmax, but it goes through multiple channels. So each one of these channels describes one of the paths, the effect of one of the coefficients. So for example, the first path corresponds to this first integral, which basically means that it's the DC value of the current. So you can think about this as a bank of filters, right? So there's the first path is a filter around DC that passes stuff around low frequency. The second bank is a filter that passes stuff around the frequency of oscillation. The third path passes stuff through the second harmonic, right? Around the second harmonic. So each one of them captures stuff around one of the integer multiples of the oscillation frequency, integrates it, goes through an ideal integration, and then adds them all up to produce the total phase. So this is probably a better picture to show the evolution of phase noise inside an oscillator, evolution of noise. So what it shows, this picture again shows the same equation, but in a pictorial fashion. So it shows that it's the noise in the vicinity of integer multiples of frequency of oscillation, and at offset delta omega from each one of these integer multiples, plus and minus, that would combine and get weighted by these coefficients, C0, C1, C2, C3, and so on, to produce the spectrum of the phase. Now, the spectrum of the phase does grow without bounds, because it's an ideal integration. So at 0, it does go to infinity. And you may ask, how can it go to infinity? So it means that it will have infinite power. Yes, the spectrum of phase can have infinite power, because it's just a measure of the deviation in time. There's no physical energy stored in deviation in time. It's just like an error in timing. It means that your error in timing is, in essence, unbounded if you wait too long. But the spectrum of the voltage cannot. And what happens is that the nonlinear process of PM will flatten out this top in such a way that you can easily show that actually the total energy underneath this thing is constant. So the more phase noise that you have, the lower the top will have to become, so the total area underneath it becomes the same, right? So if you have the same amount of output, the more phase noise you have, the lower the top would be, so it becomes broader and shorter. And in the limit, of course, if you have no phase noise, it becomes an impulse, but with the finite, again, with a fixed amount of it. Now, the key thing is that these Fourier coefficients are responsible for the changing of the noise. So if you think about that, and if you try to find out what the process looks like, is that then what you have, the white noise at any of these frequencies, C1, C2, C3, the fundamental, second harmonic, third harmonic, would translate to 1 over f squared, because of the integration, right? You're looking at the power and integration, so you get 1 over f squared. And then your low frequency noise, the red curve here, right? What it does is that it takes the white noise and becomes 1 over f noise, but at the omega of 1 over f, it transitions to 1 over f cubed because you already have a 1 over f squared noise. And through integration, you get 1 over f squared, so you get total of 1 over f cubed slope. So the key question is that where is this omega 1 over f cubed corner? How is it related to the omega 1 over f? And the answer to that is relatively straightforward. It's when the power of all these blue curves, right, added equals the power of the red curve, right? So the total power due to the white noise becomes equal to the power of the 1 over f noise, and that allows you to calculate. And you can see that the omega 1 over f cubed, when the total output power spectrum is this black curve, which is sum of all of these, right? In linear, this is a log plot. But so what happens is that at that point, the sum of all the other ones is equal to that, and that allows you to calculate what that corner would be. So now the question is, what is that? First of all, what is that corner? The key question is that, and you can calculate it to show that that corner now, this corner, omega 1 over f cubed corner, is proportional to the device 1 over f noise corner if you had one noise source with 1 over f. And if you have multiple ones, you have to just aggregate them and see where it is. But the proportionality factor is actually C naught over gamma RMS, the ratio of the DC value of the ISF to the RMS value. So now, in devices like MOSFETs, for example, the 1 over f noise can be pretty large and prominent. And if that is the case, what happens is that this noise can be pretty dominant and it can cover a lot of stuff, and it can basically just dominate your phase noise. So you're interested in reducing this effect to the extent that you can. And how would you reduce that? So, well, to reduce this, the good thing is that it gives you a knob to turn, C naught, right? The DC value of the ISF. So it says that if you want to minimize this upconversion of low frequency noise, 1 over f noise, for example, is you need to minimize the C naught. You need to minimize the DC value of the ISF. So let's see what affects the DC value of the ISF. So in some applications, if you think about the DC value of the ISF is simply given by this integral, right? It's the averaging of the ISF over one period, which is 2 pi. And now think about this scenario. So imagine, for example, you have a ring oscillator where you have symmetrical rise and fall time. So the rise time and fall time are about the same, which basically means that the positive and negative lobes of the ISF will have about the same shape and same magnitude. Now, if, for example, you have a scenario where the rise time is very slow and the fall time is very fast, what would happen? What happens is that when the rise time is slow, it will be more sensitive, right? We saw this, that if the slope is smaller, you have more, the same change in the voltage would produce a larger change in time. And also you're sensitive for a longer period of time. So it results in a lobe that's a lot taller and wider. And on the other hand, if you actually, and then you have a fast drop, for example, you will get a negative lobe that's shorter and thinner. So you can clearly see that the one on the right will have a larger DC value than the one on the left. And this can be tested experimentally, right? So for example, you can make a ring oscillator and change the ratio of the devices. Typically, because NMOS and PMOS have different, the mobility of the holes is between half and 1/3 of the electrons in typical devices. You usually make the PMOSs twice as large, or 2.5 times or 3 times larger as the NMOS. But if you take one of the stages and do the opposite, you can imagine that it will have its output will have a fast fall time and a slow rise time. And you can try to inject into this node versus another symmetrical node and see the difference. And when you do that, you clearly see that an injection into that asymmetrical node, which is shown on the left-hand side, produces about, in this example, about 12 dB more upconversion compared to an injection into a symmetrical node. So, and then you can actually take it even farther, basically by constantly changing the ratio of the NMOS to PMOS, right? So you can actually take a ring oscillator and tune the ratio. So start changing the ratio from a smaller ratio to a larger ratio, and you will see that the C naught value, which is really the real metric, right, goes down and comes back. So if you can play with the DC value of the ISF, which is the metric you should be playing with, symmetry in this example is a surrogate for that. But in general, if you look at the DC value of the ISF, minimizing that allows you to minimize the upconversion of the low frequency noise.
Does minimizing mean, so whenever I see a plot like this and I see minimum, that means that's a symmetric point?
Well, it's symmetric as far as the upconversion. That's a good question. So the question is that this is the point where you minimize the value of C naught. So it's symmetric as far as it's optimum in terms of upconversion of noise. It doesn't necessarily mean that the waveform will look the most symmetric. It means that in aggregate, its effect is more symmetric. And that's a great question because it actually may not happen at exactly the point you may expect it, because also there are nonlinear capacitors and things of that sort involved. But the metric that you should be really looking at is minimizing the C naught, which is shown here. And then you can see, again, the waveform, if you look at the waveforms associated with these things, you can see that there's a symmetric waveform and an asymmetric waveform. And then you can see the ISF actually associated with them produces, in this example, it produces the one for asymmetric, which is on the left. Lower left shows the ISF. So what you can see here is that you have a larger DC value compared to the case that it looks more symmetrical. Now, the other interesting question related to this thing is the question of the effect of number of stages on ISF in a ring oscillator, right? So ring oscillators are oscillators that are convenient to use because they are very small in area. They're very compact. Because usually if you want to make an LC oscillator, you need to have an inductor, and we implement our inductors as spirals, and they become large. To get any reasonable amount of inductance, you get something that's very much larger than what you get from multiple inverters. So understanding the phase noise behavior of ring oscillators is useful for many applications. Now, sometimes they are not sufficient to operate for certain operations, but it's something that we can actually look at. So let's look at that briefly and see how that behavior looks like. So if you actually try to evaluate the ISF for different ring oscillators in this experiment, what we've done here is that we have kept the frequency of oscillators the same. So we have ring oscillators. These are inverters. These are inverter chain ring oscillators. So these are basically like an NMOS, PMOS inverter. Anything from with the number of stages, odd number of stages from n equals 3 to n equals 15. So you have multiple oscillators. And we've kept the frequency the same. So the oscillation frequency is the same. And what you see is that the ISF itself becomes smaller and smaller as the number of stages increases. And this should make sense, because if you think about the waveform, right, of the output of a 3-stage ring oscillator, the edges are pretty slow. I mean, the rise time and fall times would be slow. If you look at a 15-stage ring oscillator, the transitions have to be faster, right? Because otherwise you would not get the same frequency of oscillation out of 15 stages versus 3 stages. So, and which means that you have sharper edges, which means that the lobes of the ISF will be shorter and thinner, and as you can actually see in this example. So we can model this ISF, this shape of the ISF, and approximate it with the following form. So we can actually assume that they're quadratically increasing and decreasing, and we can actually assume that they have a certain slope, which we show as 1 over F max prime. F max prime is the slope. So this is basically the rise time. And there is generally a relationship between the delay of a stage ring of an inverter with its rise time. And there's a proportionality constant, which we call eta here. Now, if you think about that, this corresponds to an ISF that would be like a triangle. So we are approximating the shapes that we saw in the previous slide with these triangles. And if you look at this and plot and do the calculation based on this triangular assumptions and use the eta, what you will find out is interesting, that the RMS value of the ISF is in fact some physical constant, some constants, there's 2 and pi and something like that, and eta, the relationship to eta, and it's only related to 1 over n to the power of 1/2. Another way is that gamma RMS squared is inversely proportional to the number of stages cubed, based on this assumption. And if you actually take that and plot it versus the RMS values calculated from the actual ISF to calculate, you can see it's a pretty nice fit. So this is actually independent of frequency, because it's done with different frequencies. So in some examples, we actually did this as a fixed frequency, where we kept the frequency of the oscillation constant. And some of them we did not change, let the frequency be different. We just took the same inverters and added more. Of course, the longer ones will have a smaller frequency than the shorter ones. And you can see no matter what the frequency is, how you do it, the RMS value of the ISF is in fact only dependent to first order on the number of stages. And this is a useful piece of information because it allows us to kind of come up with some sort of a conclusion about the effect of the number of stages on the phase noise. So the question is that if I want to make an oscillator, I can make a ring oscillator. If I'm making an inverter chain ring oscillator, is it better to make it longer or shorter to get better phase noise? Because I can get similar oscillators with different designs. So let's do that. So the assumption here is that, so if you have a noise expression, which is basically the standard noise expression for a MOSFET, we are using the channel noise to approximate it. We define this delta V, which is a characteristic voltage, which is half VDD on minus VT as an average voltage. The total power consumption, including crowbar current, which is the current that goes straight through the NMOS and PMOS when they switch and doesn't charge or discharge the capacitor, will be given by 2N, 2 eta N VDD Q max F naught. And F, the frequency, is of course inversely proportional to 1 over 2 number of stages and delay per each stage. And if you take all of these things and write them in these forms and plug them into the expression we have for phase noise, we arrive at this expression for the phase noise. So the expression here simply says that, well, there's 8 and 8 over 3 eta, some constants, kT over P, the ratio of the kT over the power dissipation that you're using, so the power you have. And it's basically VDD over V characteristic and delta omega over omega naught over delta omega. And you don't see any dependence on n. There are multiple n's appearing in the number of stages, but they are canceling each other. So what is the message of this thing? The first thing that since there's no dependence on n, it means that to first order in 1 over f squared region for white noise upconversion, the number of stages doesn't play a role in phase noise. So you can actually use a larger or shorter one, it wouldn't affect it. The other things that are clear is that it says, well, if you burn more power, you should be able to get the min phase noise. And you can see that this is called L min. This is the minimum achievable, not necessarily the phase noise that you will get for any oscillator design, but if you design it properly, this is what you can get, approximately. So how can we trade power to get, basically use power to get better frequency stability or lower phase noise? Let's talk about that. Think about it. Can you think of an experiment that we can run? Let's say, how can I increase my power and improve my phase noise in an oscillator? So one way to do that is I think about if I make 2 identical oscillators, right, with the same component values, and make them node for node parallel, just attach every node to an equivalent node of the other one. Well, they would both oscillate at the same frequency and in phase because they will lock to each other, of course. But what happens is that now you have increased your charge swing, right? I mean, you have increased your current by a factor of 2, and your signal power has gone up by 6 dB, right? Because your charge swing or current swing has doubled. But your noise, think about it, the noise of the left oscillator and the noise of the right oscillator are uncorrelated with each other because they're generated from different sources. So they will add in power, right? So it will go up only by 3 dB. So your signal goes up by 6 dB, your noise goes up by 3 dB, so your phase noise will improve by exactly 3 dB. So that's one simple way you can trade it. Basically, it means that scale everything up by a factor of 2. Right? That's another way of saying that. So the reason for this lack of dependence on number of stages is that ring oscillators, if the CMOS inverters, only consume power during transitions, right? So if you're inducing transitions, it's only the number of transitions that happen. So the stages that are sitting there that are not in transition, they're not consuming any power. And that's why you have this lack of dependence on number of stages. Now, how about differential ring oscillator? What is a differential ring oscillator? It's basically a differential pair that's used as an inverter. So basically it goes switches from one side to the other, right? And then you kind of can make a cascade of these things. Again, the ISF behavior looks more or less the same. You have the same 1 over n to the power of 1/2 for the RMS value. The coefficient is a little bit different, as expected. And this is for different variations, for fixed power, fixed swing, fixed power, fixed, et cetera, et cetera. And again, you can do the same calculations, and you can go through the same analysis. making certain assumptions about the noise. The noise, now you have the device noise and also the load noise. And if you take all of those into account, what you end up with is this expression, which now has a dependence on n. So if your stages, instead of being CMOS inverters, are actually differential pairs, what happens is that now you're in a situation where your number of stages, you'd have a linear, your phase noise goes up with increasing the number of stages, which basically suggests that to get the best phase noise, you want to use the minimum number of stages for differential ring oscillators. Why is there this difference? Where is this coming from? Well, if you think about that, it comes from the fact that CMOS inverters only dissipate power when they're transitioning. But differential pairs are constantly drawing current, whether or not they're transitioning, right? You have the tail current. So as you increase the number of stages, you have more and more stages that are idle. And they're not contributing to the transition, but just burning current. So if you're operating at a fixed power, you have a total power budget. It means that you want to aggregate as much of that in as few stages of a differential ring oscillator as you can to get the best phase noise performance. Now, there's another aspect to this, which is the upconversion of low frequency noise, which is the 1/f noise, the part, which is determined by the DC value of the ISF. So you can actually do a similar calculation for asymmetrical ISF and calculate the gamma DC and gamma RMS. And from that, you will see that in fact, there is a 1/n dependence for the 1/f cube corner, which basically means that increasing the number of stages, in fact, does improve the corner frequency. It pushes the corner frequency back. So in short, in summary, you can actually think about it for differential ring oscillators, right? Your 1/f noise would not depend on the number of stages, but your flicker noise improves by increasing the number of stages. So probably a larger number of stages is better. Now, for differential ring oscillators, they go in opposite directions. Your white noise contribution becomes better with a smaller number of stages, but your flicker noise contribution becomes worse with number of stages. So the real design choice really comes to the point of which one is stronger and which one you care about in your application the most. So that should give you a sense of what these things work, how these things work. So these are some examples of prediction versus measurements of the phase noise. So these black plots show actual phase noise measurement plots, and these red ones are the predictions based on the model. So you can see that you can make accurate predictions as you go. And so that basically covers this part of the discussion. There are a couple of other interesting aspects of it that are quite relevant to the process of design, and we'll talk about those now. So let's talk about this, starting with the first concept, which is what we call the cyclostationary noise sources. That sounds like a mouthful. What do we mean by cyclostationary noise sources? Cyclostationary noise sources really correspond to noise sources that vary with time, meaning that the noise, of course, itself varies with time, but their statistical property changes with time. Now, that's in general a non-stationary noise source, but cyclostationary means that the statistical properties change in a periodic fashion. Now, what does that mean? Let's look at an example. So here's an example. Imagine this is a very classic oscillator. It's called a Colpitts oscillator, where you basically have a capacitive divider and an inductor. The series combination of these capacitors and the inductor form a tank, an LC parallel LC, and the output voltage is sampled and reduced, but an attenuated version of that is fed back, and through this common gate stage, it's basically fed back to the oscillator. So if you look at this oscillator, if you take this oscillator and simulate it or make one and measure the voltage across that, you will see that the oscillator, that the drain voltage, the output voltage, looks pretty sinusoidal. It looks pretty much like a closed, clean sinusoid if you look at this waveform. Now, if you look at the drain current of the MOSFET is actually off for most of the time. And then the drain current has this large lobe and then comes back off. So what it means is that the transistor is off for more than half of the cycle. When this voltage goes to the lowest, the source voltage goes to the lowest, the transistor turns on, injects a bunch of current into the tank, and then turns off. This is the way it actually operates. Now, if you look at the channel noise due to this process, right, what does it look like? It wouldn't look like this would be a sample of the noise in the drain, or the channel noise, right? It would, if the transistor is off, it's not going to be generating a lot of channel noise, right? Because there's no channel. to produce noise. So it only produces noise periodically when this has happened. So you can see that this noise is periodically increasing, going up, coming down again, going up, coming down again, and so on and so forth. So this would be a sample of that. The question is that what do we do with this? Can we model this thing or not? Now, if you think about a noise, a cyclostationary noise, like the one shown at the bottom of this picture, in pink, I guess, you can think about it as a stationary noise, like the blue noise, multiplied by a deterministic periodic waveform, which we can call noise modulating function, or NMF for short, right? So what happens is that you can actually think about this as this red plot multiplied by the blue plot producing the purple, supposedly, or pink, whatever that is. Now, if you think about that, so then you can write your cyclostationary noise, In of t, as the product of the stationary noise, In naught of t, and alpha of omega naught t, which is the noise modulating function. Now, if you take this and plug it into the master equation here that we have, you will see that now, if you write it as the product, you can actually have now the product of two deterministic functions. The NMF, the noise modulating function, alpha, and the gamma, which is the ISF. So now you can think about this thing as an effective ISF, as a new ISF. So you can say, look, it's as if I have stationary noise with a new ISF, which is what we call the effective ISF. So you take that deterministic modulating function and absorb it into your ISF and define this effective ISF. And now this effective ISF is what is going to tell you what the general sensitivity of the oscillator to noise is. So let's look at this example and see how this looks like. So for example, for the Colpitts oscillator, if you look at the ISF, the ISF more or less looks like sinusoid because the waveform looks more or less like sinusoid. Now the NMF, the noise modulating function, the blue curve, has this shape which is related to the shape of the current pulse. And the product looks like the red curve, which is significantly smaller, right? And if you look at this RMS value, for example, you can expect it to be significantly smaller than what you see for a regular unmodulated noise. So this is interesting because it tells you that actually if you can actually lower the effect of phase noise. So we can actually do another thought experiment here where basically this is something that you can't do. So if you take the oscillator, if you take the transistor and increase the mobility of the device, or mobility of the carriers, let's say mobility of the electrons in this case, right? And if you increase it, you will see that the lobes of the current become narrower and narrower, right? So this is a thought experiment to just demonstrate this. And as you do that, you can see the effective ISF becomes smaller, and you can translate it to an improvement in phase noise, and you can see that you can get close to 10 dB of phase noise improvement if you could increase the mobility. So in other words, if you can make your current, if you can basically line up your noise with the timing of the ISF, things work out nicely. Why? Why is this a good thing in the case of Colpitts oscillator? Because remember, the ISF, the sensitivity was minimum at the peaks, right, of the oscillation waveform. That's where your current and noise is maximum. So the maximum of your noise coincides with the minimum of your sensitivity. And that's what is captured by the effective ISF. You can see that the effective ISF is significantly reduced in this process, in this example. And that's why Colpitts is one of the good oscillators. That explains why Colpitts generally produces good phase noise behavior. This timing, this cyclostationary noise timing. Now, is this generally true? Is it true that you can actually, for every oscillator, this will reduce the phase noise? No. Here's another example, an opposite example. You remember in a ring oscillator, the transition time is the time where you have the maximum sensitivity, right? But that's when you have the maximum current anyway. So your maximum sensitivity and maximum current coincide, or maximum noise and maximum sensitivity coincide, and you can see it. If you look at the black curve, which is the original ISF, and then you take the NMF, which is the blue curve, and then you calculate the effective ISF is almost exactly the same as the original ISF, which means that there's no improvement, there's no enhancement due to this alignment. So this is a useful thing from a design perspective, and it can actually be used. Now, there's another thing, which is also kind of like so this is one of the conclusions of the design, and it can be actually used in examples of the design of the oscillators. Here's another concept that there's another corollary that comes from the modeling. One of the interesting things is that what if you have fully correlated noise sources? Now, let's say, well, how can you have fully correlated noise sources on 5 different nodes of a ring oscillator, let's say, for example? Can you give me an example where you get fully correlated noise sources, or mostly correlated noise sources? If they are coming from outside, right? So for example, extrinsic sources of noise, let's say interference, right? You can have digital circuitry running next to you and then just generating noise and all those things, and it can get coupled into your oscillator. So now they will be all correlated. Now there's an interesting trick that you can actually play if you have fully correlated noise sources. If you think about it, if you had a ring oscillator and there were 5 sources on that, basically the total phase noise shift would be the superposition of all the noise contribution, phase shift contribution of each one of them. And what this does is that you can basically just write them as the sum, and if the oscillator nodes are identical, their ISFs would be identical for each one of these sources, right? The only difference is that they will be time shifted with respect to each other, because the waveforms are time shifted with respect to each other, right? Because this is all the stages are identical, the waveforms would be the same, just time shifted with respect to each other, which basically means that the ISFs would be the same but time shifted. Now, if you take that into account and write it as different phase shift, so these ISFs are periodic waveforms, right? So let's think about what happens for a periodic waveform if they are, let's say you have 5 stages, and what happens for the fundamental. For the fundamental term, if you look at the fundamental of the first one, it would be here. The fundamental of the second one, maybe here. Let's say the fundamental of second one is here. Fundamental of third one is here. Fourth one is here, and fifth one is here, right? So what happens to the fundamental component in aggregate when you add all 5 of them? They all cancel each other out, right? So nothing is left. How about the second harmonic? So let's keep this as the fundamental. Let's say the second harmonic. For the second harmonic, for the first stage, it is here, right? The phase is doubled because it's second harmonic. This is the second one. Then you double the phase, third, fourth, and fifth. So you cancel. For the third harmonic, first one, go 3, second one, go up 3, third one, go up 3, fourth one, go up 3, fifth one. Cancel. Fourth harmonic, first, second, third, fourth, fifth, right? Cancel. Now how about the fifth harmonic? Here, 5 back, here, 5 back, here, here, and here, right? So what happens, and also the same thing with DC. DC, of course, has no phase, so they all add. So it's only, if they are fully correlated, it's only the nth harmonic, where n is the number of stages that matter, including 0. So ISF usually by the time you get, for example, if you have a 5-stage ring oscillator, by the time you get to the fifth harmonic, it's not that large. So you can try to minimize it. But the part that's really left is the DC part. So the DC part is going to stay. So the sum can be approximated as the DC part. And if you do that, then it means that you have actually a way of suppressing the extrinsic sources that come into the circuit. By making the oscillator exactly symmetrical, making the stages identical, even introducing extra dummy loads for each one of them, so to make them exactly the same, keep them in the same orientation so they pick up the same amount of noise from the supply and substrate and things of that sort. Make the connections identical. And then just make sure that you can minimize this C0, the DC value, which is a knob we can turn in the design to some extent. And that way you can actually reduce the reduce the impact of the noise into the system. So that's another discussion. So in general, if you have perturbation, external perturbation to the circuit, it is the perturbations that are in vicinity of the integer multiples of the frequency of oscillation that play the most significant role. So that basically tells you that if you don't want to have external signals, for example, there are scenarios where you have multiple VCOs or multiple signal sources running at different frequencies on the same chip. or in the same system. And they couple to each other. So in your frequency planning, you may want to think about how you arrange them so that they do not coincide with something that's close enough to your system so that it modulates it the most. Because the closer it is to the frequency of oscillation, or an integer multiple of that, the more it would modulate that. Okay? So let's. So one of the interesting things about jitter, when we started our conversation, we said that the timing jitter has two parts, right? When you think about the timing jitter, if you actually look at the timing jitter versus the time from triggering edge on an oscilloscope, right? We said that if you look at the standard deviation, or if you look at the variance grows linearly first and then quadratically next. Another way of saying that is that if you look at a logarithm of the variation, what you have is that initially the slope is going to be 1/2, and then when you go up, you get basically a slope of 1. When your standard deviation grows linearly with time. So why is that? Why do you get these two regions? We said we will talk about it later. If you think about it, it really goes back to two different things. Now, if you have transition errors, right? Let's say if you're thinking about the ring oscillator. So let's say during each transition you introduce a little bit of a timing inaccuracy, right? Timing jitter. So let's say we go through transition 1, you introduce some jitter. And then you go to the next stage and you introduce some jitter. Now, do you expect the noise of this first stage and second stage to be initially kind of like at least? If they are not correlated, if they're not related to each other, if they're like intrinsic noise sources, that, like let's say white noise source generating that, these will be uncorrelated, right? So how do you expect these timing jitters, random timing jitters that are not correlated with each other to add? You expect them to add in power, right? So they will only grow. And its variance will grow linearly, right? Sigma squared would grow linearly, so because you're adding in power. Now, if you had a correlated component, though, right, what happens? If you have a correlated component, so now, which means that if the shift is forward a little bit in the first time that I go through the first transition, the second transition is also doing the same shift in the same direction, and so on and so forth. So there's correlation. Now you will add them in amplitude, so you expect them to grow. You expect the standard deviation to grow linearly, which is exactly why you get these two regions of operation. So this is the independent part, which is growing at the rate of, with a slope of 0.5 in the logarithm plot, and the correlated part that grows linearly because you basically have these things. Now, and the question is that what can cause this correlation? There are different sources of correlation that can produce this kind of correlation. So for example, if you think about external noise sources, right, are going to be correlated. But we saw that there may be tricks to get around them. Now, internal sources like flicker noise. What is flicker noise? Flicker noise is a low, slowly varying source, right? One way to think about low frequency flicker noise is basically slowly varying offset. It's an offset that changes slowly. So now what happens is that if an oscillator is running at like a gigahertz or 10 gigahertz, right, the signal is going and transitioning doing a full circle 10 gigahertz. Now, I go through one device and it introduces some flicker noise shift. Right? Flicker noise produces a little bit of a time shift. Now, I go through 5 stages and come back, right? And the flicker noise hasn't changed that much. So now, if you think about it, so this is another way to think about it. So think about this. The flicker noise, if let's say I have a rising edge going through a 5-stage ring oscillator, right? So it shifts me forward a little bit. And then I go through 5 stages, and I come back, and going through the same stage, but this time I have a falling edge, right? Because that's the way it works. That's the inverse. So I have a falling edge. Now, the falling edge would be shifted in the opposite direction if the slope is, now, depending on how much it gets shifted, it depends on the slope, right? So let's say I get shifted back in the opposite direction, and then I go back and come back, and I get shifted forward in the forward direction. So I'm getting shifted forward, backward, forward, backward. Now, if the two transitions have the same slope, if you think about it simplistically, the total shift is going to be 0 afterward, right? But if one of them is steeper and one of them is shallower, let's say this way, what happens is that the amount I get shifted forward is more than the amount I get shifted back. So I will end up with a net shift. And this is another explanation for why the symmetry, the DC value of the ISF plays a role. Because when the DC value of the ISF is 0, or the stage is symmetrical, the amount of forward shift and backward shift are going to be canceling each other to first order. So, but these kind of low frequency noises can produce correlation, and that's one of the sources of correlation that you can actually think about. Okay, so one more way of thinking about this, which is, so now this viewpoint, this time domain viewpoint can also be applied to the injection locking and injection pulling. So this is also, so we are going to talk about this, and I'm going to talk very briefly about the work of Brian Honk, which has applied the time domain viewpoint to injection locking model of the oscillators. So this is basically, think about multiple oscillators that are connected to, they're in the same environment and they're communicating with each other. So they can actually start locking to each other or pulling each other. So let's say you have two oscillators that are sitting next to each other and running at very close frequencies to each other. One of the interesting phenomena that can happen is that if they are sufficiently close and they're sufficiently coupled, they can both lock to some same frequency. Or you can have an injection signal being injected to an oscillator, and it can shift its frequency, if it's close enough, to a different frequency that would be exactly the same as the injection, or it can be related to its harmonic or subharmonic. And why is this important? It's important in a lot of places. So for example, when you make quadrature oscillators, oscillators that generate I and Q, cosine and sine, two signals that are 90 degrees, this is important. You have phase references. You have basically dividers that operate based on this principle. You can have PLLs and clock recovery systems that will be affected by this. So a lot of systems will be affected by things of this sort. And one of the things that's important to us is the ability to be able to model this accurately. So this picture is a critical picture that you want to kind of like think about. So here, what you have is that imagine you have an RLC again, and then imagine that you have some sort of a negative resistance, negative conductance to cancel the loss of the tank. So going back to our original picture of the oscillator, you remember we said that you can actually have an injection into the oscillator so that you can, if you have an injection like this, you will not change the amplitude, but you can change the phase. You can advance it or pull it back. You can retard it or advance it, right? So what if you do this periodically? What if instead of this blue waveform, imagine the red waveform, but you do it every time it gets to this point, and then you jump ahead. So if you look at this, the red signal compared to the blue signal has a higher frequency, right? So by having a periodic injection, so now what we are talking about is, in this case, an injection happening with a certain period. And if it has the right amplitude and it happens at the right time, it can actually produce a waveform that's running at a higher frequency, right? The period is reduced. Now, the period of the oscillation, although the natural frequency of the oscillation was that of the blue one, now the period of this oscillation is dictated by the period of the impulse train. So that's one way to think about injection locking. You've made it faster. You can also do the opposite. You can actually have one, well, I should have probably made this red to correspond to that red. And then you can have the purple one, the opposite one, which basically now every time you get below here, you're pushing it up. So you can see that you can actually have a situation where you can actually go above or below. And one of the interesting things is that actually if you do the calculation of how much phase shift you induce due to this injection of charge and express it in a simple calculation, which is basically this shown in this plot and in the state space diagram, what happens is that in the state space you're moving from this state or that from this point to that point or from this point to that point, and you can calculate the total amount of deviation in frequency that you can expect and relate it to the maximum charge swing of the oscillator, which is related to its current and the quality factor. And if you aggregate all of them, you get this expression, which is the well-known Adler's equation. So this is something that Adler did in the 60s, and did a calculation not this way. He did a calculation very differently. But from this time domain picture, it naturally emerges that you can actually do these kind of things, and you can produce a locking range, so which you can see is the locking range, the range over which you can maintain locking, is related to the center frequency, of course, but it's scaled by Q, the quality factor of the oscillator, meaning that the higher quality factor the tank of the oscillator is, the narrower its locking range would be, right? Which makes sense. because the higher the quality factor it is, the more resistance it would be to a change in the frequency. It's less compliant, if you will. Right? And then also it's related to the ratio of the injected current to the oscillator current. So the more power you inject it, the harder you try to push it around, the more the more you can deviate it from its natural frequency. This is a very useful and interesting phenomenon that can be also viewed in this picture. And one way to think about that is a rotating frame of reference. So what you can have here is that there are two rotating frames of references. One is the frame of reference of the free-running oscillator, which is rotating at the rate of omega naught. Right? And then you have another frame of reference, which is the injection reference frame, which is rotating at the rate of the omega injection. Right? The two different rotating frame of references. So you can write the total phase, which is what's happening inside the cosine of omega. So instead of cosine of omega t, you're writing cosine of this little phi of t, or omega naught t plus phi of t. You can write it in two different forms. You can write it either as omega naught t plus phi of t, which is the way we've been writing it for free-running oscillators when we were doing the phase analysis, which is also equal to the omega injection t plus phi of t, theta of t. So this transition allows you to analyze the oscillator in the frame of reference of injection. And what you do here is that, again, you do a similar analysis, define an injection. The only difference here is that we are defining this gamma tilde, which is essentially gamma divided by Q max. So to make the equations more simpler, we are writing gamma tilde, which things in terms of gamma tilde, the scaled gamma, which is gamma divided by Q max. So you get Q max doesn't show up in the expression because it's absorbed into the gamma. And when you do that, you can write an expression describing the overall behavior of the oscillator. So you can see that there's a differential equation that describes the deviation of the phase, which can be used to analyze the locking, or can be described to analyze the pulling, where an oscillator is not exactly locked, but its frequency is kind of like deviating constantly back and forth because of this external perturbation. So it's resisting it, and it's not completely there. And in the case of injection locking, this equation simplifies to the case where basically the d phi dt, the rate of phase change, has to be 0 in the locked frame of reference, right? That's by definition when the locking occurs. And when you put that in, you will see that the maximum locking range, can be defined using this, what we define the lock characteristic function, this capital omega of theta, which is the time averaged over one period of gamma times the injection current. And what this means is that, so the key takeaway from this is that the locking characteristic is determined by the time average, one period average, of the ISF, the impulse sensitivity function, and the injection current. So why does this matter? Because it allows you to do design. First of all, let's see how it looks like. So for example, in this plot, on the right-hand side, you have a situation where the locking injection frequency is around the oscillation frequency itself. So you're trying to inject around the frequency of oscillation, not much higher, not much lower. And what you see is that if you look at the ISF, or the scaled ISF, the blue curve, and the injection, which is in this case sinusoidal, you can see that the amount of the total net product will have a positive part and negative part that over one period integrate to 0. Right? So this is when you are near the frequency of oscillation. Now, in the case on the left-hand side, you're injecting above the oscillation frequency. Now, in this case, to maintain that phase shift, the oscillator has to have a product of the ISF, or the scaled ISF, and the injection current that's positive at all times. And you can see the lining has to happen in steady state so that this product is large and positive all the time. And conversely, in the middle, what you see is that when your injection frequency is below, actually, sorry, the other way around. On the left-hand side, the injection frequency is above the oscillation frequency. And in the middle, the injection frequency is below the oscillation frequency. And then you can see that, to maintain an average, which is shown with this dashed green line, and that's negative, you need to have they have to be in opposite phases. So if this is what determines how much the locking range happens, you need to ideally optimize the shape of the injection current in such a way that it matches what? So this is a key design question. If you wanted to maximize the locking range, so let's say you wanted to maximize, let's say you're using the locking range for something useful, let's say an injection lock divider or something like that. What does it tell you about the shape of the injection waveform to maximize this product for a given amount of power? Well, it says that it should be matching the shape of the ISF, right? So it means that there should be a matching between, so there are multiple, if you think about this, this is the space of all the possible injection power, right, sources. You can have multiple different kinds of waveforms going into your oscillator. But if you're trying to maximize the injection, if the shape of the injection matches that of the ISF, that would be the optimal. Because that would give you the largest product integrated over one period that would produce the maximum locking range. And that's an important one if you want to, and conversely, if you're trying to minimize it, of course you need to make sure that the same thing applies. Now, the developed theory is a lot more general and broad, and it applies to harmonics and things of that sort, and it models the harmonic and subharmonic injection. And I invite you to read the two papers, the twin papers that are describing this, if you are interested in this in more details. But one of the applications, for example, is that it allows you to, for example, design a dual modulus divider, one that can actually switch between the divide by 2 and divide by 3 by proper design of the waveform and proper design of the injection waveform. And this is an example of this oscillator, this divider based on this concept. So you can actually, what you can do, you can make a divider that divides by 2 and divide by 3 with the same output frequency, which is a useful thing if you're making a PLL. And these are some of the example results. Okay, so any questions on this?
The LC oscillator, we can find the result, the ISF analytically.
Right.
So how many different kinds of oscillators? Is it very, very difficult to find analytically for any of these different kinds of oscillators, or how many?
So yeah, it's not very difficult to calculate the analytic. It depends on the kind of oscillators. For some of them are more difficult, but at the end of the day, you will probably run a simulation to get an accurate model of the ISF, because your ISF will depend on the dependence of the capacitances and then all of the nonlinearity of the device itself. So it's all of this captured in the ISF. And because of that, most often you may not want to do it analytically, but generating it in a simulation is a pretty straightforward thing. The way it works in the simulator is that you hit it with this impulse that's not too large to kind of drive it into nonlinearity, and then you just sweep that impulse, and you just need probably 10 points across one period, and you can generate those off of that. So that's the easiest way. But there are ways to analytically calculate what the ISF would be that we can discuss offline probably.